Hello everyone. We are now going to begin our lecture on section 2 of chapter 2, which is the chapter on set theory. Here we are going to talk about subsets, which really is a part of a larger set. So sets that are a part of a larger set. So in this section, we are going to define what subsets are, how to recognize whether a set is a subset of another set, and also different types of subsets. So essentially in this section, we are going to define and be able to recognize subsets. We will also learn to determine and recognize proper subsets, which is a special property of subsets, and then determine how many subsets we can create from a given set. Let's first try to define what subsets mean. It says here set A is a subset of set B, symbolized as A, and this particular symbol here, which is like a horizontal U with a dash under it. So A would be a subset of B if and only if all elements of set A are also elements of set B. So that means that the elements in A will be the elements of B as well. Now, that doesn't mean that A and B are equal or equivalent sets. B could be a much larger set than A. However, as long as the elements in A are also present as elements of B, then we can say A is a subset of B. Now the symbol A is a subset of B. This particular symbol indicates that set A is a subset of set B. Okay, so that's a definition and the notation we use to indicate whether a set is a subset of another set. Now, a few other rules and notations to know about subsets is that the symbol A and then the symbol for subset crossed out with a diagonal line means that A is not a subset of B. So the symbol A, not a subset of B, indicates that set A is not a subset of set B. So just remember this symbol. It's quite easy to remember. It's just that the symbol for the subset is crossed out. It tells us that something is not a subset of another set, right? Now, another thing is to show that set A is not a subset of set B, one must find at least one element of set A that is not an element of set B. So if set A has any element which is not a part of set B, that means set A is not a subset of set B. All right. So we'll go through some examples of this. So let's go through this example of determining whether set A is a subset of set B. So set A is given to us as boat, train, plane. These are the elements in set A. And let's pull up set B. Set B has boat, train, plane, and automobile. So we have to go ahead and check first if all the elements of set A are also in set B. So yes, boat is there in set B. Train of set A is also there in set B. Plane is there. Automobile is not in set A, but that's fine as long as the elements of set A are in are all to be found in set B, then we can say A is a subset, and this is how we are going to write it. A is a subset of B. All right. However, B is not a subset of A. All right. So it's not commutative, so to speak. All right. A may be a subset of B as in this case, but B is not a subset of A because B has the element automobile, which is not in A. All right. Let's pull up the next solution here. It says here all of the elements of set A are contained in set B, so A is a subset of B, which we also figured, right? Now we'll talk about a special type of subset called a proper subset. So what is a proper subset? Here's a definition of it. It says set A is a proper subset of set B, symbolized A is, and you indicate a proper subset as this horizontally placed U, but there's no line under it. So A, this reads as A is a proper subset of B when, if and only if all of the elements of set A are elements of set B and set A is not equal to B. That is, set B must contain at least one element not in set A. All right, so that tells us it's a proper subset. So as an example of proper subsets, let's go through this instance here. A, the set A has the following elements: jazz, pop, and hip hop. Let's pull up set B, which has uh, classical, jazz, pop, rap, and hip hop. So is A proper subset of B or not? We scan through the elements in set A and B, and we see that B and A are not equal sets. All right, there are some extra elements in set B. So we have, what do we have in B which we don't have in A? The classical, the element classical, we also don't have the rap. So all the elements of A are a part of B, of the set B, and B has a few extra elements as well, which makes them unequal. They are not equal. Therefore, we can say that A is a proper subset of B. Let's pull up the solutions quickly and see what they have to say here. Okay, all the elements of set A are contained in set B, and sets A and B are not equal. Therefore, A is a proper subset of B. All right, so here B has a few extra elements which are not in A. That's fine. We say A is a proper subset of B as long as all the elements of A are present in B and B has a few extra elements which make the sets unequal. All right, they are not equal. We can conclude that A is a proper subset of B. How about this example here? Determine whether set A is a proper subset of set B. Let's pull up the sets. The set A has these letters here, A, B, C, D. Let's see how set B looks like. B has A, C, B, D. And we see that all the elements of A are also there in set B. They are not in the same order perhaps, but the elements in set A exist in set B, and we see that both are of the same size. There are no extra elements in B. They are equal sets. So this tells us that A is not a proper subset of B. All right, so A is not a proper subset of B. A is a subset of B, but it is not a proper subset of B. All right, so let's pull up the solutions now. Solution A, here A equals set B, so A is not a proper subset of B. All right. Now we're going to learn how many different subsets we can possibly create out of a given set. First of all, to determine the number of distinct subsets possible from a given set, we can mathematically use this formula here, 2 to the power n. So the number of distinct subsets, distinct means unique subsets, all right? Number of distinct subsets of a finite set A is 2 to the power n, where n is the number of elements in set A. All right, so what we are trying to do essentially is, let's say we have a subset called A with all these elements A, B, C, D, E. So what we are trying to do is create subsets, smaller sets from this larger set. All right, we have to see how many of those are possible. So there could be one set which is maybe just A, another one C, which is A, comma B, comma C, another one, let's name another one which is just the letter B. All right, so we can create all combinations of these elements and call them subsets. All right, and doing this, how many different subsets can we get? We will know right away by using the formula 2 to the power n. So n represents the number of elements in set A, in the original set that we are working from. So here this has 5 elements. So the number of possible elements we can get, or not elements, the number of possible subsets we can get is 2 to the power 5, where n represents the cardinal number of the original set A. So 2 to the power 5 would be 2 times 2 times 2 times 2 times 2. So 4 times 2, 8 times 2, 16 times 2, 32 unique sets can be obtained from the set which has size 5, all right, a cardinal of 5. So the number of distinct subsets of a finite set is 2 to the power n. Let's see what. Now the number of distinct proper subsets is given by this formula. The number of distinct proper subsets of a finite set A is 2 to the power n minus 1, where n is the number of elements in set A. So previously we saw that the number of subsets, distinct subsets, is just 2 to the power n, but number of distinct proper subsets is 1 less than whatever 2 to the power n evaluates to. So if we came up with 32 as our possible subsets, then proper subsets would be 32 minus 1, 31. All right. So this is an example where we will be applying the formula we learned about calculating the number of distinct subsets. Not proper subsets, but distinct subsets. So we will have to apply the formula to find the number of distinct subsets. And in the second part of the question, they ask us to list all those subsets with their elements. All right, so we will handle the second part later on. Let's work on the first part, where we just give the number of distinct subsets that can be created out of this list of 4 elements S, L, E, D. So let me take out my pen here. The formula for the number of distinct subsets was 2 to the power n, where n represented the number of elements in our initial subset from where we will be creating the different subsets. All right, the initial set from where we will be creating all the different possible subsets. So n here is 4, correct? N is 4. So this value of n is going to be 2 to the power 4, which means 2 times 2 times 2 times 2, which is 16. So there are 16 possible subsets that can be created out of this set of SLED. The second part says list all the distinct subsets for the given set SLED. So we have to spell out, we have to clearly show all the all the subsets with their elements. All right, and we will do that in the next slide, but I will also give you a process to find all the subsets without missing one. All right, so let's go on to the next one, which will display the subsets that can be created. So for part A, since there are 4 elements in the given set, the number of distinct subsets is 2 to the power 4, right? 2 to the power n was our formula. So we replaced the n with a 4 and we multiplied 4 2s. So 2 times 2 times 2 times 2 is 16, and that's exactly what we got for an answer as well. For the second part of it, here are all the different subsets that can be created out of the initial set. The first one is SLED. That means the subset, all right, this is, remember, this is not a proper subset. If this was a proper subset that they had asked us to create, then the first one wouldn't be there, all right? So, however, since this is just possible subsets, distinct subsets, we have to include the initial subset as well, which is SLED. And then we have subsets with 3 elements in it. So SLE, SLD, SED, and LED. And then all the subsets with 2 elements in it. So SL, SE, SD, LE, LD, and ED. And then the subsets with 4 elements in it, the subsets with 1 element in it, all right, there'll be 4 of them, is what I meant to say. So S in one subset, L in one subset, E is in one subset, D in one, and then there's also the empty set, all right? So all of these together are 16 possible subsets that could be created from 4 elements of SLED, and we have all the subsets listed out here. All right, so I'm going to now show you how we can create all possible subsets without missing any of them. All right, now here I'm going to give you a method which I call the tree method, because I'm going to create trees to capture all possible subsets that can be created out of this set of elements SLED. So recall that we said there were 16 possible subsets that can be created. All right, so we'll go one by one. The first one would be this SLED, correct? The set is also a subset. So let me write that here. The first one would be SLED. That would be one subset. Let me surround it with braces. Now, from the second one, I'm going to list all the sets of size 3. All right. that can be created out of SLET. All sets of size 3 is what we are going to create. So what I'll do here is I'll start with S, all right? Start with the first element, and then, so I'm going to write here an S, and then after S, we can either get an L or an E or a D, correct? We can either get an L or an E or a D. After L, all right, we can either get a E or a D. After E, we can get a D, all right, and the last one drops off, all right? Sorry, not this one. The last one is the one with the D. This one drops off. So now we have combinations of size 3 starting with S. So I'm going to walk this tree now and list all the combinations: SLE, SLD, SED. So let's write that S, and we have to put our commas in our roster form of the set. So SLE 3 is the third one is SLD, SLD. Fourth one is SED. All right. So all I did was I walked this tree once I created a tree with 3 elements in it. All right. So now that we are done with all possible combinations starting with S, we have to go to L. All right, so if L is the first draw, all right, if we get an L for the first element, then the second element could either be a E or a D, all right, and then the third after the E would be a D, okay, and then after the D, there's no other element, so the last one will always fall off the tree. All right, so this one we will not include. So what do we have here? LED. So the fifth subset is LED. LED. So now we are done with all combinations of size 3, from the initial set. All right. Now we have to go on to creating trees with 2 elements in it. We are going to follow the same process, but instead of this third branch, we are going to stop at 2. All right, so let's erase this to make some space. All right, and then we again start with S. So we are going to start with S. So after S, we can either get an L, either get an E, or a D, correct? Following S, we can either in the second draw, we can either have an L or an E or a D. So let's list those. Number 6 was SL, SE, SD, correct? Now we have to start a tree of size 2 with 2 branches from L. So let's do that. L. After L, we have an E or a D. All right. So I'm going to list those 2 combinations, LE and LD. So we have L, E, and 10 is LD. All right, and then we have to start another tree with E this time. All right, so let's do that. E. After E, we only have a D, correct? We only have a D. So our 11th subset is going to be ED. Let's write that. So number 11 is ED. And we are done with all combinations with 2 elements in it. So now there will be a set of combinations with 1 element in it, right? Let's see one thing here though. Yeah, so let's erase the trees so we make some space for the other subsets now. Okay, so 11 was ED. So now we have to create subsets with 1 element. That's easy. You do not need to create any trees. I'm going to just write the different elements as separate subsets. So the first one is S, number 13 is L, number 14 is E, number 15 is D, correct? And then we have one last, which is going to be an empty set. Include that one. All right. So here we have all the different subsets created using the tree method. Essentially, you're using the tree method for for the ones which are less than the initial subset, which has elements less than the initial subset. All right, over here we used it for 3 elements and 2 elements. We don't really need the tree for when the number of elements is just 1, correct? Here I'm going to show you a technique of coming up with all possible subsets of a given set using what I call the tree method. So I'm going to create trees which captures all different combinations possible of the different subsets, and then we will traverse the tree to get all the elements that we can put in a subset. All right, so the different subsets that we can create from this set SLED would be subsets of 4 elements, 3 elements, 2 elements, 1 element, as well as the empty set. An empty set is also a subset of a set. All right. So we'll start by laying out the subset with 4 elements. Remember that the set is also its own subset. All right. So I'm going to write the first subset as whatever I have for the set SLED, and there's only one subset with 4 elements in it. All right. Then from the next one, we will create subsets of 3 elements. All right. So what I'm going to do is over here on the side, I'm going to show you how to use the tree method. So again, we are going to have elements of 3 in each subset until we capture all possible combinations of 3 elements. All right. So we'll start with the first letter here, S. So let's do it here. So I'll start with S. All right. So take the first letter, and then after the first letter comes L. So in the second draw, we can have either an L, all right, or an E, or a D. All right. Then from L, again, this is a set with 3 elements, we have just captured 2, so we have to go another time. So from L, what are the 2 possible combinations? You can either get an E or a D, right? So I'm going to put an E or a D. Now after E, what can you get? Which element can you pick? A D, correct? So I'm going to write a D. And then the last one, there's nothing after D, all right? So this one will drop out of the tree. This will drop out. And I'm going to list all these different elements by traversing the tree. So we'll have one set which is SLE. Let's write that. Okay, so subset number 2 is SLE. Subset number 3 would be SLD, correct? We are traversing the tree, SLD. So that's another combination. I'm going to write that, SLD. So here we are capturing subsets with 3 elements in them. Then we have SED, correct? So let's list that. 4 is SED. But we are not done with combinations of 3 yet. We have to do another tree starting with L. We've captured all the combinations starting with S of 3 elements, but now we have to continue the process starting with L. All right, starting with L and the letters that come after it. So I'm going to start that tree here. All right, so it's L, start with L, and then what comes after L? It's an E or a D, correct? And then for the third draw, for the third pick, after E you can get D, correct? So I'm going to write D. For the D here, what comes after D? Nothing. So this drops off the tree. This drops off the tree. So what combination can we get starting with L? LED. So let's list that. 5 LED. And now we have captured all the subsets with elements with 3 elements in it. All right. So there are 4 of them: SLE, SLD, SED, and LED. The next one is an E, but there aren't 3 elements after E. There are only 2, so we don't need to build a tree starting with E. All right. So now we go to creating subsets of 2 elements. Let's start that, and before that I'm going to erase this tree here to make some space. But this time we are going to create trees with just 2 elements. Again, I'm going to start with S. So you have to start over the process. Start with S. So I'm going to start with S. And then after S, we can either get an L or an E or a D. Now, you don't need to go any further because we need only 2 elements. So SL, SE, SD. Let's list those. So number 6 is of 2 elements, SL, and then number 7 would be SE. Again, use your parenthesis, SE, and then 8 is SD. SD here, right? We are walking the tree. So SD. All right, but now we have to again start a tree, this time with L. So LE, LD, let's do that. So starting with L, here we go, L. In the next row, we can get an E or a D. All right, so LE, so number 9 will be LE. And then 10 will be LD. So we are done with all combinations starting with L. We go to the E. So create a tree with 2 elements. So starting with E, the only element left is a D, right? So number 11 will be the subset ED. ED. So now we are done with all combinations of 2 elements in them, all the subsets which would hold 2 elements. So now the next one is subsets with 1 element in them. So again, let me erase this tree so we can make space for subsets with 1 element. So number 12 would be for those for subsets with 1 element. You do not need to create a tree. All right, you just list each of these elements separately in roster form. So S, and then number 13 is L, number 14 is E, number 15 is D here, D, and the last one, number 16, would be the empty set. All right, so this is how you can go about creating all subsets from a set without missing out a combination of elements in a set. All right.